let's talk about an important problem in computer science known as the P equals NP problem. So I'm only going to give kind of a high-level picture of this, but it'll capture, I think, the most important points, though it will omit many important technical details. So here's a surprising fact. An efficient solution to any of these three problems, 3SAT, which we talked about in an earlier lecture, independent set, which we talked about in an earlier lecture, and longest path, which is the procedure for finding the longest weighted path in a weighted graph. Turns out that any solution to any of those three problems, if it's efficient, would also give an efficient space-time bounded compression algorithm. So in other words, what I'm saying is that if you can solve longest path, you can also find it gives you an efficient algorithm for doing what we call the space-time bounded compression process. So why is that? Well, it's because space-time bounded compression reduces to 3SAT, to independent set, and to longest path. And by reduce here, I mean the notion that we talked about in an earlier lecture, and which I'll show you graphically in a moment. Now, not only does it reduce to these three problems, but it actually reduces to tens of thousands, at least, of other related problems. So let me give you an example of what exactly I mean here, right? So let's say X is, so I'm defining X as, does there exist a Java program that outputs this picture, and it is of length 20,000 or less, and it produces this output in fewer than 1 million executed lines of bytecode? That's the thing I want to do. Well, it turns out that this statement in English, very surprisingly, can be transformed into a longest path problem, or a 3SAT problem, or an independent set problem, or more. So visually, let's see that. This is the problem that we're starting with. This is, I want to compress this image with this many bits using this many bytecode lines of execution. So if I feed that to my preprocessor, it builds some kind of long graph, and then it's a weighted graph, that is, and then it's going to call my longest path solver if one exists. Then I'm going to get back a path which has a weight greater than W. Then I'm going to post-process that. And the reason I'm saying this is that's what longest path does. It gives me back a path of weight greater than W. And then I am going to run a post-processing algorithm, and I will get back Java code of length 20,000 that outputs HugPlant and this many executed bytecode lines. Now the actual graph that exists here and the processing steps are going to be phenomenally complex. And if you're curious about how the reduction works, see 170. But really shockingly, this problem of compressing this plant into 20,000 bits, where the decompression procedure needs to take 10 million lines of bytecode execution, can be cast or transformed into a longest path problem. Now, one thing I said earlier you might have found confusing. Why am I saying path of weight greater than W rather than longest path in the graph? I will cover that in more detail very briefly soon. Okay. So how do we know that X can be turned into a longest path problem? That is, like, what is this insane fact that I'm claiming? That seems preposterous. Well, I'll give you the short answer, and it's going to use jargon you've never heard. So it's because that X is a problem in the complexity class NP, and therefore we can reduce it to any NP complete problem, which includes the longest paths problem. Now, I haven't introduced some of the terms here, like what NP or NP complete means, but we'll go over them briefly in a moment, but it's going to be too quick to make complete sense. The longer answer is that you should see the class CS170 if you want to really deeply understand this, but I'll give you a brief understanding of these terms now. So this brings us to P equals NP. So there's two important classes of yes-no problems out there that I'm going to talk about now. One of them is P. These are efficiently solvable problems. And then there's NP. And these are problems who have solutions that are efficiently verifiable. So I'll give some examples. So here's some problems in P. Is this array sorted? That's very efficient to solve. How about, does this array have duplicates? Well, that's also a very efficient problem to solve. Now you'll notice something important. These problems I'm stating are yes-no problems. Okay, that's just how P and NP are defined. And if you want to really go into a lot of detail, it'll be CS170 that does it, but we're only thinking about yes-no problems. Let's see some problems in NP. So one of them is, is there a solution to this 3-sat problem? So I give you a specific instance of 3-sat, which you'd have to go look at that previous lecture to know what that means exactly. And the answer is yes or no. Another is, in graph G, is there a path from S to T of weight greater than K? Now, the reason I'm calling this an efficiently verifiable problem is that if you give me a solution to it, I can very quickly check. You give me a path, I just add up all the weights of the edges and I find, okay, yeah, you're right. That weight is greater than K. So it's in that sense that I mean it is efficiently verifiable. Or for 3-sat, you give me an assignment to the variables that says that the 3-sat problem is true. I plug them in, I see if the answer is actually true, and there you go. Now, technically, I should mention that NP problems are those for which a yes answer is efficiently verifiable. There's a separate set of problems known as co-NP, and it's the no version of that, but I don't want to go into that. This is 170 and other stuff. So let's see some problems that are not in NP. So, for example, if I'm considering a bunch of moves in chess, if I say, is this the best chess move I can make next, right? Like I have a specific problem in mind and I'm saying I'm going to move my queen here or whatever, that is a very hard problem to verify in general, so it's not an NP. It's not something I can just look at and say, yes, that's the answer. Another example of a problem is, what is the longest path in this graph? That's not a yes-no question, so it doesn't count, even though it's very closely related to what we're discussing. Okay, that's as technical as I'm going to get for P equals NP, so let's move on. Now here's a totally shocking fact. This one should blow your mind. Every single NP problem out there reduces to 3-sat. So that includes bounded space-time compression. It is a yes-no question. That is, bounded space-time compression is a yes-no question for which a yes answer can be efficiently verified. You just take the program that was output, you run it for T cycles, you see if you get out the bit stream you're supposed to. So every single possible NP problem, it reduces to 3-sat, and this is way beyond the scope of what I can possibly talk about today. But if you're curious, I have linked the Wikipedia article to the theorem that proved this. Now, what this tells us is that, a little bit informally, but any decision problem for which a yes answer can be efficiently verified can be transformed into a 3-sat problem, or, as it turns out, a longest paths problem, or, as it turns out, an independent set problem, or others. And it turns out also that this transformation itself is efficient. And by the way, if you're curious what efficient means, that's polynomial time. Okay, but I'm just not really going to say much more about it. So, a question was posed by Stephen Cook, who is the Cook who is from this theorem that everything can be reduced to 3-sat. And Stephen Cook said, are all NP problems also actually P problems? In other words, are all problems with efficiently verifiable solutions also efficiently solvable? And this is often given as, does P equal NP? So the reason you might think the answer is yes, what I imagine Cook was thinking, is, well, it's really easy to check a given answer. Like, someone gives me a putative solution, I can easily check, is it good? And so maybe with the right pruning rules, something like a KD tree or some other data structure, we can kind of zero in on the answer, only explore the parts of the space that matter. And if you want a more thorough treatment of this problem, see CS 170. But that's what the P equals NP problem is all about. If you can check a solution very quickly, can you also solve the problem really quickly? Okay? And the specific definitions for what I mean by efficient, those will have to be living in CS 170. And so in the next video, we'll tie this back to compression, but just wanted to lay out the landscape so at least you had a little bit of an idea of what the P equals NP problem is all about.